And with Luca from Scuola Superiore Sant'Anna, we present you hierarchical constant bandwidth server with deadline servers. So the goal of this work that we are presenting is to rework the RT group SCAD to use deadline server. The RT group SCAD is essentially the scheduling of control groups through the real-time policies, scheduling policies. And so one first question that comes up is if it is being used somewhere.
So the answer is yes. Only recently one of the switching guys managed to randomly enable it with secret 3.2 or something like that.
Okay.
So RT group SCAD works now?
I don't delete it.
Yeah, we are asking because
Being used.
Okay. Yeah. Scary.
we are asking because until some time ago, for example, it was disabled in PM13. Force disabled. So
Well, it might still be disabled.
okay.
And also distribution that we want.
It's not.
No, the thing is, people keep telling me it's broke, but no one explained to me what exactly is broke.
The whole theory of it is broken.
Forget it.
The whole concept is broken.
It might be. Anyway, so I enabled it as people who tested this is doing what you want. And most of them either didn't came back and said, yeah, it's okay. And I was okay, so I enabled it for everyone else. And Clark came to me and said, it's not working. I said, what's not? It's not working. You didn't explain exactly what's wrong. Everything.
So we want to rework the RT throttling mechanism to use the newly introduced deadline servers. This removes code duplication that uses SCAD deadline. This also avoids the deferrable server issue where we have that two consecutive runtimes and weird time slices and so on.
Okay, yeah. So
This is, you want to use the deadline server for RT, right?
Yes.
yeah, to schedule RT runqueues. Yes.
Okay, and then the other thing, I thought the group scheduling code was deleted or something since.
I want to.
You want to delete
But
it.
I've never been able to because there's always just one or two idiots who say, no, we actually use this crap.
Okay, great.
Okay. So I'm going to just say a few words about this example just because it comes from real-time theory. So assume, for example, you use the real-time throttling and you say I give a runtime of 900 milliseconds every second. So one person may expect that fair tasks can execute for 100 milliseconds every second. But here in this strange example, we have more than 1 second of time in which fair tasks cannot execute. Just because here a real-time task wakes up, so it sets the period, the throttling period, consumes just a little bit of runtime and then blocks and wakes up at this point. Here it can consume all the runtime. Here a new period starts and can consume again all the runtime. So you have this large amount of time, which is much larger than the period you set, and in all of this time, fair tasks cannot execute.
That looks like a feature.
Sorry?
I said that looks like a feature.
A feature?
Yeah, but it's a feature, not a bug.
I don't know. I would say I would see it as something a little bit surprising because I naively expect that when I set, let's say, 900 every second, I expect fair tasks to be able to execute 100 every second.
Well, but it's within that period. It is working. It's just, yes, if you put two periods together, there's going to be a gap there.
Yeah, but the point is that here we have this long amount of time, which is larger than one.
But you could,
okay,
you could use the fair server, you could configure the fair server with a shorter deadline.
Sorry?
The deadline server for
No, but that's the theoretical thing. So
this is theoretical.
yeah. So don't get into.
This is using the deadline server, correct?
No, this is with the current throttling. If we use the deadline server, when it wakes up here, a new deadline is generated,
Yeah, we do
so
that
we don't
for,
have this issue.
We do that for the pair server right
That's
now.
one reason why you say that.
Oh, okay, so when it wakes up, it's the start. So
Yeah.
Okay.
So basically, our idea was maybe it's useful to have this runtime check when waking up as done by the deadline. Okay.
And so that is the deferrable server?
No, this is the old RT.
Right.
Yes.
What is the deferable server?
Oh, the deferrable server is just the real-time jargon for this kind of behavior.
Right.
So the current throttling is working as a deferable server.
Yeah, that's what I was trying to learn.
Sorry.
Okay.
You can go.
So another idea for this work is to also have non-throttled real-time tasks, and so one idea that we propose is to have the FIFO RR tasks in the root control group without runtime control. With this work, we also have better control. We could also have better control for the time we allocate to each control group. In fact, we could reserve a different runtime for each core. And an interesting idea is to also have unprivileged usage for the real-time tasks inside the control groups. So you know that to use the real-time scheduling policies, you need super user access. Instead here, since the runtime will be limited, we could also give unprivileged access to these policies. So there was a previous prototype which was implementing this idea, and this modified the sched deadline to use these control groups. So the sched deadlines schedules each control group, and then the tasks inside the group are scheduled using fixed priority scheduling. So this is compatible also with containers in general and with every container orchestrator. And so the results here are a hierarchical scheduler, where we have the sched deadline as the root scheduler and the FIFO RR scheduler as a second level. We associate a runtime and period to each virtual CPU, and we remove the runtime migration feature that was used in the previous implementation. And so we have the implementation for compositional scheduling, a compositional scheduling framework. It supports multiple CPUs. As said, we have an implementation that has the same runtime and period for all CPUs, but it can be easily improved. And so we have this with this main scheduler that dispatches the control groups, and we have global fixed priority scheduling for each control group. So we have this hierarchy where we have a host and a guest scheduler. They do not talk to each other, so there is no need to implement communication. And when at the runtime of one of the virtual CPUs of the local control group goes to 0, we can migrate tasks to all the other virtual CPUs. So we can share the CPU time.
This assumes no affinities.
Sorry?
This assumes that all tasks are free to migrate.
Yes.
Yeah, of course, we respect the affinities. Yeah. This is, if the affinities allow migration, then we can migrate. Otherwise, we don't migrate. Yeah.
So if I remember correctly, the moment you introduce affinities, a whole bunch of the guarantees go out the window.
Yeah, are more complex. Let's say, yeah.
Well, it's NP complete, so that complex.
Yes.
Okay, so how it is implemented, we have the scheduling entities for the scheduling classes. Generally, these are associated each entity to a task. Instead, here we use the deadline entities to, we associate them to runqueues. So we have a deadline entity for each virtual CPU and a runqueue for each deadline entity. And so whenever a deadline entity is selected, there is no single task associated. We have a group of tasks, and we run we get the highest priority task from its run queue. And so the general idea is to modify the DL entity structure to include this a pointer to the run queue. So we also modified the C group task group structure so that it also contains the run queues and the deadline entities, one for each virtual CPU. Of course, the deadline entities are pinned one to each single physical CPU.
So you don't do the minimal concurrency thing?
Sorry?
So if a server has a bandwidth of an effective bandwidth of 1.5 CPU.
No. We consider servers only with less than 1 CPU of bandwidth. We can have multiple servers, so the total is larger, can be larger than 1 CPU, but each single server has a bandwidth which is smaller than 1.
Do you have like equal bandwidth or more? Like if you have 1.5 CPUs bandwidth, is that like 75 and 2 CPUs?
Yeah, yeah.
Yes, so you have equal bandwidth for all CPUs spread, but there is also a possibility to balance it differently if necessary.
That doesn't necessarily work correctly. Suppose the composition is a FIFO task that is expected to run 0.8 and another FIFO task that is 0.4. And you only give them 2 budgets of 0.7. Then the 0.8 task will either be forced migrated or not be able to run to completion because it gets throttles.
Yeah, so this implementation was originally based on some theory from real-time literature, which says after executing for some time, one of the 2 tasks has to migrate to the other CPU. Now, we'll talk about this later. We have some extensions with respect to that theory. So with the current implementation, we have a last part of the patch set in which we can assign different utilizations to different CPU cores. But that was not in the original patch set.
Okay. So as said, the pick next task call of the scheduler selects one of the C group's DL entities, the one with the earliest deadline, and then the scheduler is recursively invoked, so we don't have code duplication, but this time on the local run queue of the control group. So this is the idea of the hierarchy. We have these physical CPUs, and each container has the same number of virtual CPUs, and each of the CPUs has a bandwidth and a period. And so we have the host scheduler, which is deadline, which schedules these virtual CPUs, and then whenever this is deemed runnable, we pick tasks inside the container to run on the physical CPUs. So in the previous patch set, this was implemented manually. Now, of course, we have deadline servers, and so we can exploit the new infrastructure to create this scheduling. And so when we interface deadline server with C groups and with their specific run queues, we get that we have deadline servers for the M deadline servers, one for each core in the control group. We set the runtime and the period through this control group interface. And we have, for each deadline server, set one local run queue. This is different from the actual usage, the current usage of the deadline servers, because we have one deadline server per core. The run queue is the global run queue. And there is this different deferred behavior. So for the deadline server for SCAD fair, the deferred behavior makes running the fair tasks at the near the end of the deadline. We don't want that here, but we want to run the DL servers as soon as the new deadline kicks in. And so by creating this two-level hierarchy, we are compatible with the real-time theory, the compositional scheduling framework. So we can do some real-time analysis on this. Okay.
Okay, I go.
Yes.
Okay, so what we have right now. So we basically re-implemented our previous patch set using the deadline server infrastructure. So previously we had let's say our own implementation of what the deadline server does in a better way. So we switched to the deadline server. Right now we have a patch set which is based on 6.13. Yuri worked on 6.9, then we forward ported it to 6.13. So one of our first question is if there is interest in having this kind of approach for mainline. If there is interest, of course, we can rework our patch set, forward port it to JIT master or to tip sched to whatever is needed. Right now, the patch set, we tested it with the Linux test project just to see if it crashed. It works, seems to work correctly for most of the tests. Then Yuri implemented a lot of, let's say, stress tests, which were just continuously moving real-time tasks from different control groups or changing priorities or changing affinities just to check if everything worked. And this seems to work correctly. We also used RTApp or applications similar to RTApp composed of multiple periodic real-time tasks. We used some theory from real-time literature to perform schedulability analysis, and we verified that the results we get with RTApp are consistent with the schedulability analysis. So at least real-time theory seems to be happy with our implementation. Of course, this doesn't mean that we don't have bugs. We didn't find any huge bug in the current implementation. Maybe there is something which still needs to be fixed. What can this be useful for? Of course, the original idea was to run Docker or Kubernetes containers containing real-time tasks and make sure that one container is not going to interfere with the execution of other containers. Another idea is to run multiple independent real-time applications on the same machine. If we look at the traditional real-time scheduling, in order to guarantee the respect of deadlines of an application, we would need to know all the other applications running on the machine. Using this approach, we can guarantee a group of tasks independently from the others. And then I just realized that maybe this approach could be useful also for parallel tasks modeled as graphs or something similar. So we put all the threads of a DAG inside the control group. We can assign a CPU bandwidth to the control group. The control group can execute on multiple CPUs, and we can schedule the threads with real-time priorities inside the control group. So maybe this can be useful for this kind of thing.
So,
yeah.
The case where you have two CPUs, each for the server of 0.6, and an overcommitted FIFO set, a 99 task that does 1, and a 50 task, or less than 99, that does 0.5.
Okay.
If you do the concurrent thing, it will try and run 99 and 50 concurrently, thereby exhausting the time for the second part of the 99 to run it. So then you violate your FIFO scalability rules.
Here in this case, the FIFO schedulability rule, FIFO schedulability is more complex because we have a two-level scheduler. So there is a different analysis, basically.
So Anderson, he did this some years ago, and he said that if you do the minimal concurrency, so basically you compact your entire servers into the minimal number of servers. So if you have, instead of 2.6, you have a 1 and a 0.2,
Okay.
then the FIFO scalability rules are preserved.
Okay, because you partition. Okay, if you partition the tasks, so you fix some tasks on one core and some tasks on the other core, then you give one full core to some tasks and half of a core to the other tasks, maybe, yeah.
In that scenario, your FIFO 99 task, your most hierarchical, you can run to its fullest extent.
Yeah.
Then the rest can be consumed by the lesser priority tasks.
But you said that the bandwidth per CPU is configurable, right? You can have like...
Yeah, this is one of the extensions we are going to put.
So if you offset it, at the moment you are overcommitted to your FIFO, which might not be considered a schedulable set, but it is a set that has well-defined rules within FIFO, in such that the 99 should get all the time once and then 50 gets whatever is left. Even if you offset it, by concurrently running to 50, you will have consumed too much of the combined bandwidth for the 99 task to still run to completion.
Not if you have configured the bandwidth correctly, right? That's what I thought Luca suggested.
No, so that's the problem. We have overcommitted to FIFO, but because FIFO does not actually have a concept of bandwidth, you cannot know. But so if you have within your task set a task that requires more than one CPU of this,
Okay.
then the concurrent task of lower priority can exhaust the bandwidth of the...
Yeah, you have to allocate more bandwidth, yes.
Yeah.
So yeah, in case of, let's say, hierarchical scheduling, so a server and tasks below the server, you end up with an overallocation of the bandwidth. So if the total bandwidth of the tasks is 1.5, you can need to allocate 1.8, for example, in order to respect the requirements. Yes. That's one bad part of the theory, yeah. Okay, so here I'm talking about some of the decisions we took when implementing these. Some of these decisions are kind of arbitrary, so we would like to discuss these decisions to understand if they are correct or if we should redo the thing in a different way. So the first one is about the tasks migration. So consider a simple example, a control group with only two tasks, with only one task, sorry, and we set a runtime of 10 milliseconds with period of 100 milliseconds, and we have, suppose, two CPU cores. So the question is, how much should this task be allowed to execute? 10 milliseconds every 100 or 20 milliseconds every 100. Right now, the current implementation of the real-time group scheduling has this feature, which is runtime share, which kind of migrates the runtime from one core to the other. So if we have one single real-time task and we reserve 10 milliseconds on two cores, when the task executes for 10 milliseconds, the runtime from the other core is migrated to this core and it can execute for 20 milliseconds. This kind of breaks the real-time schedulability analysis, but this also can cause starvation. Consider the case in which we allocate 60 milliseconds every 100 milliseconds on 2 cores. When a task executes for 60 milliseconds on one core, we migrate 40 milliseconds from the other core, so the task can execute for 100 milliseconds every 100 milliseconds, and the core is starved.
I think at that point you wouldn't get more than the 95. Yes, it would take time, but you would not exceed the overall limit.
I don't know. I tried to look at the code, and it seemed to me that it migrates up to 100, up to the period, but maybe I'm misunderstanding it.
I think it's risky. I think that we're going to that just say run, so yeah, potentially you can start. Okay, that's bad.
Anyway, our proposal was a little bit different. So instead of migrating the runtime, we migrate the task. So after the task executed for, of course, if the affinity of the task allows migration. After the task executes for 10 milliseconds, we move it to the other core where it can execute for other 10 milliseconds. So the task can execute for a total of 20 milliseconds every 100. This feature is implemented in let's say, a second part of the patch set. So we have a first part which implements just interfaces the deadline server with control groups and use this for scheduling 5 or round-robin tasks without this kind of migrations. And then we have a second part of the patch set which implements this kind of migrations. Yeah.
I'm not fully familiar with the patches and the design, but like, I guess I'm wondering that why about starvation? Again, I'm coming back to the fair server. You have the fair server, you'll never let, like...
This was before that.
This was before that.
Yeah,
but you're talking about patches.
Yeah, what I described there, the starvation is the current behavior without the patches and before the fair server.
Okay, but you said you're going to post patches, so that's what I was wondering. Okay. So you don't need the second half of your patch set. You don't need the second half where you're migrating the task to another core just so it
I'm not sure. I think it might be still needed because if you migrate, let's say that you with your thing you migrate the bandwidth to a different CPU.
We migrate the task.
No, yes, but what he's saying that maybe you don't need that, and you migrate you either migrate the bandwidth, but if you migrate the bandwidth, then you can overcommit a CPU. So you get into other kind of trouble, even with the deadline server. If you let the task run and use bandwidth from some other CPUs, okay, I think you can still overcommit one CPU.
So you're saying that you would borrow all the bandwidth for the...
I mean, this is for essentially not wasting runtime in the group. So either you migrate runtime or you migrate task, but I think if you still migrate runtime, even with this, it's still subject to issues. So.
And also, if we migrate runtime, multiple C groups will try to.
Yeah, when we have multiple C groups, we could have issues migrating the runtime.
The monotonic limit is 0.7, right?
Yeah, the schedule, the utilization base, yes.
So if we inflate the actual usability of a particular workload by the inverse of 0.7 and give this as a combined runtime, which I take as the runtime times the number of CPUs, is it then guaranteed to correct the schedule?
Unfortunately not, because the 0.7 is for a rate monotonic without any kind of scheduling hierarchy. When we have first, let's say, a server which schedules the fixed priority tasks, then this number decreases, unfortunately.
It becomes hard to make a utilization only based test, because in this case the time granularity of the real-time tasks crosses with the granularity of the deadline server.
So I'm worried on how people are going to have to configure this.
But that's also true for scale deadline. If you want to use it properly, you need to do
analyze a single task, and you can analyze a single task. But for FIFO, you have the bigger problem that you don't have at best you can sort of measure.
You can shift the schedulability analysis tool in the current source space.
No.
We have plenty of them.
So I was thinking that if you measure the complete utilization of, say, a single cycle and then inflate it, then it might be...
It's more complicated because these periods have to be considered, I guess, the half periods that fit with one another. After all, the compositional scheduling framework uses this demand, offer the single time or time, these two proofs that are the demand bound and the supply bound functions. But it's a complicated analysis. It doesn't go just, with the utilization.
It's not too complicated, but it's not as simple as utilization. Yeah.
And just a comment that as in the previous patch, as Luca said, we could also have this customization of the runtimes per CPU that we had in the...
Yeah, we're coming to that.
Oh, you have something. No,
it's one of the next slides.
The additional thing could be that considering this migration, I mean, theoretically, one could think of on the fly saying what is the maximum runtime I could borrow, I could move without breaking schedulability.
Yeah, so
we might have something like that. I mean,
Daniel wanted to do partitioning first and then do this on top. I don't know. I mean, it might not be more broken than what we currently have. Who knows?
Of course, not migrating indiscriminately, so just that you have all the stuff migrated, but just, we could actually compare, okay, given the current situation of the CPU, probably it's not fully subscribed with that nice stuff. So we can compute what is the maximum runtime before migrating the task. But probably we have complexity here.
Yeah. So this was one first, let's say, questionable thing, this migration. The other thing is the extension Tommaso mentioned, and the one you also asked for. Basically, the possibility to assign different runtimes on different cores. So our first motivating example was, let's assume we have a server with 40 CPUs. If we give runtime 10 milliseconds and period 100 milliseconds, we end up allocating 10 milliseconds on every CPU, which is a lot and is a waste of reserved time. I don't think the application will have 40 threads. So we implemented a mechanism for assigning different runtimes on different CPU cores. And of course, if we set the runtime equal to 0 to a core, that core is excluded from the real-time control group, let's say. To do this, we invented a software interface. So we created this new RT multi-runtime US file, which is similar to the CPU RT runtime US file. The difference is that instead of writing a single runtime here, we can write a runtime followed by the description of a CPU set, which indicates the set of CPUs to which this runtime applies.
So if we go with C group V2, which has a unified hierarchy, you can combine the runtime controls with the CPU mask and CPU set.
Okay.
To limit this.
So another question though, why do you need the CPU mask? I mean, let's say you only have 30 tasks on this.
Okay.
Why don't you just do the math and divide it by 30 and allocate that by default, because you cannot run more than 30 CPU cores. Do you need to know which cores you should be running on from the user, or can you make that decision yourself?
Sorry.
Yeah.
Sorry, just to tell you, I think what you, if I understand correctly, if you use the CPU set thing of the C group, you can say, so this C group has this CPU set mask, like 1 to 10, and then you allocate that amount of battery on just those 10 CPUs. So probably you don't need the CPU set there because it's already part of the C group.
So it's only for C group V2.
Yeah.
Control.
And those
Why
are
do you even need
because, for example, you can have a container application you want to run on like a particular set of
Sure,
CPUs.
and at that point in time, it's a different story. But what I'm saying is, let's just talk about a default case where you don't have a CPU set. Let's say you have 40 CPUs, but you only have 30 tasks. You know you cannot run on 40 CPUs. So why not just set it up for 30 by 30?
The problem is, sorry, maybe I didn't describe it correctly. When you create the control group and you assign a runtime, that will will allocate the runtime on the.
Correct.
Yeah.
What I'm suggesting is, if you know you can keep dynamically scaling that depending if you have more tasks than number of CPUs available to you, then sure, you divide it equally between all of those. But otherwise, if you have fewer than the number of CPUs, why are you reserving on every single CPU core to start off with?
So you suggest to use the C group occupancy to scale this one.
Yeah.
So you know how many tasks are in your C group
Okay.
and not exceed that many CPUs for your allocation. But then you don't know which CPUs because
Yes, but do you need to know which CPUs is the question.
for bandwidth allocation you probably do.
Okay.
One is dynamic, no? Because that's
Yeah. One reason we wanted to specify the CPUs is that on every CPU we have to respect the sched deadline admission test. So the sum of the servers running on that CPU core should have a bandwidth smaller than 1. So when we create a control group, if we don't specify on which CPUs to allocate the bandwidth, the kernel would have to do some kind of best fit, first fit, whatever algorithm to decide on which CPUs to allocate the runtime. In this case, by specifying the CPU cores, we allow the administrator or whoever to do the math, to do the bin packing, let's say, of the utilizations, so that we don't overload anything.
I think that is the correct thing to do for almost 90% of the use cases. But for somebody who does not want to maybe do this analysis, but still want to use your other option is you might
want to do the analysis, gets to keep the pieces.
Sorry.
This is real time. It's not police.
Anyway, when we look at
But
these,
the other option you're giving me is that I keep migrating, right? My other option is when I exhaust my runtime on CPU, then I migrate to a different CPU that has available runtime.
You'll get migrations anyway with this.
Why did you get migrations if you have actually done the analysis properly and impacted properly?
because of, let's say, global scheduling. So we have, let's say, 3 real-time tasks, and we have only 2 cores, let's say, and maybe to use the runtime efficiently, the scheduler may need to migrate. So one other issue is that the amount of runtime, if we want to guarantee the respect of deadlines or temporal constraints, the amount of runtime depends on how many cores we are going to use. Unfortunately, the theory tells us that if we allocate runtime on more cores, we need more runtime. So let's say we have an application, we know that doing some math, we can know that the application tasks are schedulable correctly on 2 cores with, let's say, 20 milliseconds on every core. If we go on 3 cores, we may need to give, I don't know, 15 milliseconds on every core. So giving some control on this was, let's say, good for controlling how much CPU we allocate. But yeah, the idea of doing this in the kernel, if I understand well, your idea is the scheduler can decide where to allocate the runtime and how much. Yeah, we look at this.
And also, just to reiterate, I think what Guido was saying that so there is already an interface to specify essentially a subset of CPU, which is a CPU set controller.
Okay.
So maybe you don't need the full interface, you just need the runtime, and then you.
Would that affect SCAD-FAIR as well?
What?
Would that affect the SCAD-FAIR tasks as well? If the unified CPU interface?
The SCAD what? Sorry?
The SCAD-FAIR tasks.
Yes,
the
I
set
guess
is
you
a
don't
full
want
task.
to SCAD-FAIR task in that C group in that case. So I guess you create a C group, you assign a CPU set, and then you get 5. Yeah. So yeah, there might be already an interface, I think. But
And one last thing, so this is all assuming that we need either to allocate the same amount of time on a subset of CPUs, or just maybe on all the CPUs on a subset, but the same amount of time. So I guess we don't see with a use case where we want different non-zero runtimes on different CPUs.
We can write multiple times. So
you
let's assume I want runtime 10 milliseconds on CPU 1 and
sure,
sure 20.
the CPU sets he was talking about would not have a single runtime. But with this interface, you can have different runtimes on different subsets of CPUs in case there's any issues.
So, returning to your original example.
The mean affinity.
I forget if CPUs, do CPU set files, no, C group files, do they allow multi-value things?
some of them, I think they do.
So if they do, we could extend the runtime file to have a single value, meaning single value over the CPU mask, and a multi-value, comma separated, to mean value per CPU.
We use that in your patch. In your patch, we were exactly writing a comma separated list of numbers in the multi-runtime.
Yeah, but we can use the same file maybe.
Your mask can be cleaner.
But I mean, if you, so the C group feed, you might want and the CPU mask and different values for
For the mask. Associated that to the mask. Okay. 40 core CPUs, you don't write 40 numbers. Your mask will be
you should write as many numbers as you have bits set
in the mask. Okay. Yeah, makes sense.
Now to abbreviate zeros with none. So you get comfortable.
By the way, in an old OpenStack variant where we were doing this for big servers with many cores, we were doing this mapping of the hierarchical CBS, utilization of the CPUs. So we were doing this in the allocator of OpenStack. So the user space doing all this stuff. So in the end, we were choosing on which CPUs we wanted like a quad-core virtual container to be deployed.
And OpenStack was okay.
No, we didn't. We never submitted to that. I mean, of course, it was running on a non-standard kernel, so we couldn't propose that.
Okay, so next questionable decision we took is basically the theory, the scheduling theory considers a two-level scheduling hierarchy. We have a server and then a FIFO scheduler. And control groups really have a much deeper hierarchy. So we decided arbitrarily that only leaf control groups can contain tasks. So if a C group directory contains some subdirectories with other C groups, this C group directory cannot contain real-time tasks. And real-time tasks can only be in control groups that don't have any other children control groups.
Suite 2, you can only have them in.
Yeah, right. It's already.
C group suite 2, you can only have tasks in leaf.
Okay. So this is okay. Good. Okay, so other thing which Yuri already introduced previously, the tasks we put in the root control group is kind of special because if we put a real-time task there, it's not subject to runtime enforcement. So this allows having small 5 or round-robin tasks which will not be throttled or will not be suffer because of runtime enforcement.
Will they be and will they enforce the global throttling, like the whole 95%?
Yeah, you have the.
It doesn't exist anymore.
Oh, it doesn't exist anymore?
You have the DL server thing.
With our passion, no. So that's because, for example, some time ago I found some how-tos about preempt-RT saying if you want a short latency, please disable the throttling. So instead of disabling the throttling, which is kind of a bad thing, I think you can put directly the tasks in the root control group. And this also is a way for having some real-time tasks in the root control group. Some Linux distributions we have seen that try to put some RT tasks in the root control group, which was not allowed by our rule. Only leaf control groups can contain tasks. So
that's the C groups.
The root group is special.
okay.
For main controllers, it has magic rules.
Okay.
Yeah, that's fine.
Okay, so that's it. Okay, so conclusions. We have this patch set which works for us. Our idea was to try to understand if there is interest in integrating part of the patch set or some functionalities like this, and we can work on that. That's it.
Yeah, I think, especially with people now trying to enable this for secret v2, this might be a better way forward.
Yeah.
And then hopefully we can delete the other crap.
And also this is hopefully only for C groups v2.
Yeah, I would make this a C group v2 only.
Yeah, I think you
there is no point.
are doing this on C groups v1.
Yeah, for some more.
Yeah,
now we
only C groups v2.
Okay.
Because
We look at how to make it work only with Vision. Okay.
it should be simple.
Okay.
So I have a question.
Yeah.
So what happens when you set the bandwidth and the deadline admission control fails? Like,
Oh, you cannot write in the runtime. You are not able to write in the runtime file if it.
what's that?
Oh, but write to the file returns an error.
Or easy or something.
But you would have written, I guess.
Yeah.
You would have written to the previous state. So if your previous state was 0, you were trying to increase it, and you increase it too much or beyond.
Okay.
You could get me dizzy.
Okay.
Yeah. And the same is if you try to do set-sched 5 for round robin for a task which is in a control group with runtime 0, it will fail.
Yeah, you can unstick tasks and improve that.
Yeah.
All right. Thumbs up.
Okay.
Thank you.